let's talk about volume. Really, this is a continuation of our conversation from class on Friday. So this is volume continued, and the types of examples we'll do in this video are actually using the same two functions. So I have one example here and down here. These same two function kind of setups were used in rotation examples where we rotated around the x-axis this way. But what we'll do here is rotate them about the y-axis, so the shape spins this way instead, so it kind of comes out and behind the table and around again. So you generally take the same approach to computing the volume of that shape, but you want to integrate with respect to y in this case instead. So anytime you're rotating about the y-axis, you're going to integrate dy with y values and y functions. Alright, so this is the first shape that we'll start with here. So I have a graph of y equals the square root of x, and we're going to take the shape trapped between that graph, the y-axis, and then y equals 2, and we're going to rotate it about the y-axis. So we're imagining it's kind of pinned right here, and then this point is going to kind of swing all the way out and around, so it ends up making like this really big like saucer shape. So we're going to make the 3D shape over here. We end up with sort of a mirror image on the other side, a round edge at the top. Like that. So this thing, when we cut it vertically like we're used to, nothing really special happens, but anytime we rotate this way, we're going to cut it across this way, and we still have our circular cross sections. So let's kind of take a peek here. So if we cut it across at a particular y value, what we have is a perfectly circular cross section. So it would have that little bit of depth, which is our delta y. So this is at a y value. Its height would be delta y, but we can skip that part and jump straight to the integral, where the delta y just becomes the dy of the integral. So again, we want to think, okay, if I cut it at some particular y value, what is the area of this circle at the cut? Because that area function is what we want to integrate from 0 to 2 in this case, because 2 is the top y value. Okay, so we need to know the area of that face. So that would be pi r squared, of course, because it's a circle. So we really need to identify what the radius is at any particular y value. So this is the key. Because we rotated about the y-axis, everything should be in terms of y. So the radius of this circle is the distance from the center out to the edge. And in the picture, that's the distance from the y-axis out to this function here. But that's the x value, right? That's the horizontal distance to this point at a given y. So we don't want the square root. We want to say y squared, right? At any particular y value, that distance is y squared. And this is going to be a pattern overall. So when we rotate about the y-axis, the very first thing you might do, aside from drawing your 3D shape, is solving all of your equations for x equals a function of y. Because you know that when you get to this point, everything will be in terms of y instead of x. So because we want a horizontal distance, it's the x value that goes with that y, which, like we said, is the y squared. Okay, so my area is pi times y squared, that's the r squared, which simplifies to pi times y to the fourth. This is the function that I want to integrate. So my volume will be the integral of that function, dy. And now I want to take my top and bottom y values, which are 0 up to 2, because 2 is the very top edge of that shape. From here, integrating this goes the same way that integrating always has. It's just a y instead of an x. but we would do, okay, the pi comes down, y to the 4th becomes 1/5 y to the 5th, plug in 2, plug in 0, and then subtract. And we get, this all goes to 0. Here, 2 to the 5th is 32, so I have whatever pi times a 5th times 32 is. We could turn that into 32 over 5 times pi. It's a perfectly fine answer. Of course, you definitely expect these answers to come out positive because we're talking volume. You should never get a negative or a 0 answer. Okay, let's practice one more rotating about the y-axis. This is exactly a shape that we used in class today, where we have the 2D shape that's trapped between y equals x squared, which does continue over here, but we don't really care, and then the line y equals 2x. So there's kind of just this little shape in between here. We can tell that these two curves intersect at 0 and at 2, and at 2 they both have a y value of 4, so I have that labeled. So in class, what we did before was rotate it this way, and it kind of made like a funnel shape with a cone exterior. But this time we're going to rotate it this way about the y-axis. So this flat edge is going to make the inside of our shape, and the rounded edge will be the outside. So it's going to kind of look like a bowl on the outside, but then on the inside there's like a perfect cone shape. So we'll have symmetry this way. Okay, rotate it. So this is not the world's greatest picture, but it should hopefully be enough to get by. So again, because we rotated about the y-axis, we know that everything is going to be in terms of y, including the way that I cut the shape. So I'm going to look at cross-sections this way instead of this way, right? So if we rotate about the x-axis, your circles are this way. The y-axis, your circles are this way. So if I take a cross-section, I would end up with kind of a donut shape again. And the official name for this is washer. If you're familiar with what a washer is, you probably see why. But it's sort of like a DVD shape, right? Because it has that like hole in the middle. So if we turn this to look straight at us, so we kind of cut this open and then tip it to look at it, we would see this washer shape. And again, I'm giving it a little bit of depth just for clarity of what we're looking at, but we don't have to worry about the depth of the shape itself. So this will be at some particular y value. And we may have learned, right, in the previous example, when I was talking about the radius, trying to get the function to integrate, I put in the x equals a function of y version of my formulas. I'm going to need something similar down here. So right away, just to make it easier on my brain, I'm going to solve both of these for x. So this one becomes x equals the square root of y, and this one becomes x equals 1/2 y. Just solving them for x. Technically this is plus or minus, but if we're talking a distance, we don't have to worry about that. Okay, so we want the area of this cross-section. Anytime we set up a volume equation, we're trying to integrate the area function for any given cross-section. So we need this guy's area. So the area of this donut shape is going to be pi big R squared minus pi little r squared. So this would be the area of the big outside circle minus the area of the inside circle, which is missing. Okay, so big R is going to be the distance out to the outer edge, and then little r is the distance just to that inner edge there. Alright, so both big R and little r are going to be determined by what y value you're at, right? Because if I cut it way up here, they're actually really close together, and down here it kind of gets puffier, and then they get closer together again. So these are both going to be functions of y in this case, and these are our two candidates here kind of volunteering themselves. So we're going to look back at the picture and say, okay, well, big R is going to be, let's actually do this in a third color. Big R would be the distance from the y-axis all the way out to this edge here, this distance. So I'm going to use the expression for the curvy curve, that outer curve here. That's the, that's the square root of y1. That's this shape here. So specifically we're using this because at any particular y value, that is the x that goes with it to make this larger distance here. So my inner radius, little r, that's going to be the distance from the y-axis just to the straight line. And again, it's going to be a function of y, so we're going to use the 1/2 y from right here. So you can think of it as the x value that goes with that y, or think, you know, I'm clearly going to the straight line, and I know everything has to be in terms of y, so I'll take the y expression. Alright, so just like before, we'll kind of plug these two things into their spots, simplify a little bit if it's there, and then we'll have the function that we need to integrate. Right, this does clean up a little bit. The square root of y squared is just y. This becomes a 4th y squared. This is the function that we want to integrate, dy, and we just have to decide what our maximum y values are to complete the integral. And that's actually filled in this picture here. We're going to go 0 to 4 because 4 is our top y value. So the volume of this shape that I crappily drew over here is the integral from 0 to 4 of this function. dy. This one I won't actually compute the final volume number, but from here the integration works the same way as it always does. Pi y integrates to pi times y squared over 2, etc. Plug in the 0 and the 4 and you should have your number.